Matthew Clark, and I've been involved in delivery of transport systems for many years. I want to highlight some lessons learned from the delivery of systems and technology, and I hope that I will shed some light on the challenges of applying systems engineering in the transport arena. The key challenge in using case studies for lessons learned, it is very difficult to find them. People and organisations are happy to talk about projects that go well, and I will be doing that. However, it's more challenging and informative to discuss those that go wrong for political, commercial, and legal reasons. You know, people are unwilling to share, and you'll note from some of my examples that I'm a little circumspect about some of the projects for just such reasons. This is just not unique to transport, but what is frustrating about transport systems is the lack of overt systems engineering approaches to delivery. It's possible to identify how systems engineering processes are used, but it's rare to find a project that has been delivered from initiation with systems engineering at the heart of its delivery ethos. I'm hoping I can illustrate that. So I'm going to be looking at a range of case studies, some of which I've been involved with, not all of them. But I just want to start by showing you this 2x2 case study, a collection of case studies which appears in the CBOC guide, and you can look it up. So there's a range of different systems engineering deployments there. Only one of which, as I can see, relates to transport, which is the taxi scheduler. And I was intrigued that it's been identified as a high degree of difficulty and high degree of complexity. And so it comes above the Saturn mission and satellites. So if anyone tries to say that transport isn't rocket science, well, no, it's worse than that. Anyway, moving on. The first one system I want to look at, it's not a highways project, it's the Jubilee Line extension, which is 1999. I was involved with it as I was the validation manager for the communication system based in Neasden. Here you can see the control room externally and internally for the Jubilee Line extension. Now, this was extended the existing Jubilee Line east from to create a Stanmore to Stratford service with 28 stations. Innovations included platform edge doors and moving block signalling. Construction started in '93, but was delayed when tunnel collapsed on a contemporary Heathrow Express tunnel project, which was using the same tunnelling process. And the signalling system proved over-ambitious. And by 1999, the project was regarded as nationally important because it was essential to support the Millennium celebrations focused on Greenwich, which was one of the stations on the line. The line was opened in stages during 1999, but without the moving block signalling, which took another 10 years. Systems engineering processes and principles were used in parts, but it was clear that integration was poor. It is difficult to identify whether problems lay within the realm of project management or systems engineering. And this is a recurring theme in these case studies about whether the problems lie in project management or systems engineering. But it was clear by 1999, London Underground had outsourced project management to Bechtel, which was probably significant in the subsequent meeting the delivery objectives. From my own lowly perspective in the project, I was aware of challenges in training operators, coordinating subcontractors, and site access. It's not possible to say whether a more rigorous application of systems engineering practices and principles would have improved the delivery. However, it is worth noting that rail projects lend themselves more readily to systems engineering because of the regulatory and operational constraints forcing suppliers to act in concert. Moving on to talk about a comm scheme. Now, this was a project that went wrong for the Highways Agency, but I give them credit for actually doing the analysis afterwards, working out what went wrong and resolving the problems. It was the delivery of a new communications system in the relatively early days of the traffic officer service. So this is in about 2007, 2008, I think. And both operational and project delivery organisations within the Highways Agency had not fully developed their mechanisms for handling upgrades and improvements. The failure for the deployment of this system was manifesting in a large number of complaints from operational staff that the new system did not provide them with appropriate headphone volume to do their job. Even after adjustments, they were very unhappy. And even when it was just demonstrated that the system performance was the same as or better than previously, they were clearly not happy. And it was subsequently relatively straightforward to identify that the real problem was the fact that they hadn't been consulted properly or engaged properly during the delivery. And a systems engineering approach would have ensured that their needs were identified and taken into account, and that they took proper ownership of the delivery. And subsequently, changes were made to make sure that has happened. But I would be intrigued to know whether there are lessons learned from the CHARM deployment. Moving on to ticketing, which may not appear to be initially relevant to the automotive sector, but perhaps it could be looked at more of payment schemes. I've highlighted three different projects here. Two of them were unsuccessful. The first one being SEFT, which is the Southeast Flexible Ticketing. I wasn't involved with this, but the information that I've gleaned is available from a National Audit Office report that focuses on the challenges being constantly changing objectives and governance. However, you can also pick out from that report that there were problems in engaging with the operators, the train operating companies in the Southeast. Some of them actually got fed up and deployed their own back office, which made creating a central office to do the same thing just made it almost impossible to deliver. The national scheme that I've identified here was a success. It delivered largely what its scope required, and it's the reason why we can now use barcodes or smart cards across the rail network, and that was delivered with some systems engineering principles applied. The requirements were clearly established. When I was working on it in the validation side, we did actually introduce better requirements management for them. But generally that was a success, and system engineering thinking probably played a part in that. The regional scheme was, well, it was challenging. Any regional ticketing scheme outside of London, it's always going to be challenging, particularly if you're dealing with bus companies, because there's so many of them and they all have their different needs and requirements. And the one that I was involved with here, which I can't really say which it is, was eventually it was cancelled. Well, the funding was cancelled for it. It's difficult to say whether there was a project management or a program management issue, but I can say that we got all the systems engineering side of things fairly tied down. So just getting systems engineering right doesn't always guarantee the success of the project. But perhaps it was too ambitious from the perspective of meeting all of the user requirements. There were too many stakeholders to do it justice. I'm going to look at Dartford. The case study that we looked at earlier on in the breakout room mentioned Dartford, and I worked on what was called Dartford Free Flow, which was the removal of the toll booths. And for the northbound traffic, that didn't make much difference. The operational interventions were probably lower for traffic crossing the bridge, but for southbound traffic using the tunnel, some of the operational interventions were carried out at the toll booths by the operators, and since they weren't there anymore, a system had to be developed to do that. And I'm referring there to removal of from the traffic for non-compliant vehicles, hazardous loads, overheight vehicles, overlong vehicles were the main concern. Generally, it was a successful project, and you can see here the complicated view there. You can see is after it was just turned on, you can see the traffic lights there that manage what was called the traffic management cell. But one of the key success factors in doing that, in achieving that, was illustrated by the photo on the top right. We set up a test site, which was an old airfield near Swindon, to actually demonstrate, a full-scale view of how it was going to work. This had a number of benefits. Probably most notably was the fact that the operators could have a go, and they got engaged. They took ownership of the system, and then they were able to contribute to its development during the trial phase. That was critical to its success. Just to demonstrate, it was possible to map a lot of the activities that we did onto the systems engineering V model. But I think perhaps if there was room for improvement, it was on the requirements management. And for such a complex system, it probably needed more than just a spreadsheet to manage the requirements. Just a quick look at some into the international scene. Again, it is difficult to find examples and use cases of systems engineering at work. The PIARC actually highlight 2 from Chile and Abu Dhabi. It is interesting to see that in North America, there is a systems engineering guidebook for ITS, has been around for quite a while. It seems to focus mainly on California. But there's, as you can see, they've also published a research program for systems engineering processes and developing traffic signal systems. So there does appear to be a more coordinated approach in North America, but it's difficult to find cast iron use case studies that are informative. It's also worth pointing out that at the top left there, that Rijkswaterstaat in the Netherlands have systems engineering guidelines for their civil engineers. And I think that's something that we perhaps need to take forward in the UK, whether our civil engineering colleagues are prepared to adopt systems engineering approach. So in conclusion, systems engineering is a curate's egg. It's in transport anyway. It's a good in parts. It's clearly not at the heart of development deployment schemes, and that probably needs to change if we're going to accommodate future deployments related to connected highways, or autonomy and energy. It's actually difficult to identify case studies in systems engineering transport. There are many successes and some failures, but evidence of systems engineering is difficult to come by. Assuming Darren this morning mentioned the ITS directive, and they, under that, we were required to issue a report every 5 years on how well we're doing with systems engineering, with ITS deployment in the UK. The last one was 2017, and it's quite a useful list of deployments of ITS. Very little reference to systems engineering. So the question is, can we pick that up in some way and actually recreate that as an exercise that we need to do in the UK anyway, but introduce systems engineering into that. So thank you very much for your time. I've enjoyed talking to you, and I don't know if there's any questions. I haven't been monitoring the questions myself this time.
So, hi, yes, I've been monitoring the questions, Matthew. Thank you for the excellent talk. It's really great to see what systems engineering means in reality on the highways, and good to know that there's very little evidence of it ever going wrong. I'm not sure why that lack of evidence is there, but you did indicate that might be because people are not sharing it. But we have one observation from Ian Gibson. He says that the Dutch systems engineering guidance for infrastructure projects is really good. And there's a link in the chat for anybody who wants to go and have a look at the Dutch SE guidance. So I've got a question about the taxis that you said. That was very surprising. So taxi scheduling is a more complex challenge than sending people into space. Yeah, what do you think it is that makes it so complex? Why did it get put up there?
Well, if you think about it, how many data items are there on the network? If you include every vehicle, every cyclist, every pedestrian as a data item, in the rush hour, how many millions of data items have you got moving around doing their own thing? Whereas if you've got one rocket going to Saturn, okay, there's a lot of bits in that rocket, but there's just one thing that you've got to think about. And I think it's a question of volume as much as anything else, and some uncertainty about the intentions and the directions and the plans for all of those data items. I think that's one of the main problems with doing anything like trying to work out how traffic is going to be in half an hour from now.
And trying to anticipate what people are going to do as well.
Yeah.
Machines moving through a vacuum are fairly easy to predict compared to people, I think. So that is a fascinating observation, and I'll certainly be taking that one.